Welcome in to another new AMP podcast. My name is Ben Dubose, and I'm the news editor with the AMP publications team. In that role, I create content for both Materials Performance Magazine and Coatings Pro Magazine, which are member magazines of AMP, the Association for Materials Protection and Performance. But here on the AMP podcast channel, we also have a Corrosion Journal podcast series, which we're aware we have not updated in a while. So today we're going to try and remedy that for our CJ audience and the many listeners from the more academic side of the materials protection and performance industry. Winston Reevey, an associate editor with the journal, he recently hosted a roundtable session in which several panelists from around the world shared their views regarding a new two-part paper series based on research from 3 global labs. It's been getting good traction on the Corrosion Journal YouTube page, so if you want, you can watch the discussion there. You can also click the link to that in the summary of this podcast. But we also wanted to give our podcast audience a chance to hear it in audio form in case that's easier. So on today's show, we're going to be playing back that full roundtable episode. As far as the subject matter expertise, again, I primarily create content for MP and Coatings Pro, so I'm not going to step on the toes of Winston and his guests related to the journal. Instead, I'm just going to turn the discussion over to them and let Winston explain the research that they're going to be talking about today. You can also read about it in the July issue of Corrosion Journal, or at the journal website, which is accessible at corrosionjournal.org, or under the media tab at amp.org. So without further delay, here's Winston and the full Corrosion Journal panel.
Okay, so my name is Winston Reevey. I am an associate editor with Corrosion Journal, and I am pleased to host this roundtable discussing a recent 2-part paper series published in the journal by a 7-author team based in 3 labs around the world, in the U.S. and in France. The purpose of this roundtable is to get some insight into the background of the work and learn why it is important. The article series published in the July 2024 issue is titled Investigation of Iron Dissolution Mechanism in Acidic Solutions with and Without Dissolved CO2. Part 1 includes the electrochemical impedance spectroscopy measurement, and Part 2 includes the time-of-flight secondary ion mass spectrometry 3D mapping, or for short, TOF-SIMS 3D mapping. I'd like to start by introducing all of the authors on these papers, beginning with the 2 principal investigators, Dr. Srdjan Nesic and Dr. Philippe Marcus.
Yeah, hi everyone. Thank you, Winston, for the introduction. My name is Srdjan Nesic. I'm a distinguished professor at Ohio University and also a director of the Institute for Corrosion and Multiphase Technology.
Philippe?
Hi everyone. I am a director of the at NRS, and my research group was distributing nuclear processes is located at Chimie Paris and CNRS, which is also Paris PSL University lab.
So the other folks that who are affiliated with the Ohio University could introduce themselves one by one.
Hello, my name is Nega Amoradigadi. I completed my PhD at Ohio University, where I collaborated with Sienna at Sorbonne University on this research.
Hello everyone, my name is Huirong Wang. I was a PhD student in Ohio University in the ICMT group, and Dr. Srdjan Nesic is my supervisor. During my PhD study, I was sent to the Sorbonne University in the LIS laboratory in Paris for almost 3 years with Dr. Alain Payehuit as my supervisor. I graduated last year, and now I'm working in the Sinopec company in China. Thank you.
Okay, so I can present myself. My name is Antoine Seyeux. I am a research engineer at CNRS in charge of the TOF-SIMS platform within the PCS team at the Institut de Recherche de Chimie Paris. And for this project, I was heavily involved in all the TOF-SIMS analysis and particularly in processing and interpreting the data.
Hello, everyone. My name is Luntao Wang. I was a PhD student at PCS Group, and my supervisor was Professor Philippe Marcus. I finished my PhD at 2020, and after that, I started my first postdoc at the group. And during that time, we started our collaboration at that time. And also for this collaboration, this give me a chance to have another postdoc at the ISMT group in Ohio University, and also the supervisor is Dr. Sergio Nesic. Now I'm working at the University of Science and Technology, Beijing. Now, yeah.
I think it's my turn. Hi, everybody. My name is Alain Pailleret. I am a professor at Sorbonne University in Paris, France. And I am also a member of the Laboratory for Electrochemical Systems and Interfaces. And I've been very glad to participate to the studies that have been published in this two-part paper. My contribution was focused on the description of iron dissolution mechanisms and also in impedance measurements.
Okay, so we'll go on to the next item on the agenda, and it has to do with when this group of collaborators began to collaborate. So I guess maybe Sergin and Philippe, could you elaborate a bit on the collaboration and a bit about the background to the collaborative study that spans the oceans?
Yes, sure. I'm very excited to actually have this roundtable and have kind of closed the circle. But I'll tell you how it all started. It was a bit of a coincidence in some way, as many good things happen. Huiru Wang, my PhD student, who was spending about half of her research time between Ohio and Paris, working with both me and Professor Pailleret, was there stuck due to COVID. Her husband, Lun Tao, who is here with us, was working with Professor Marcuse on quite two unrelated corrosion studies. They can cover that part. And towards the end of that period, there was some availability. I understood that we could use some of Lun Tao's time to extend his study and maybe cover something that we are interested in at Ohio. At the same time, Negar was finishing her EIS study on mechanisms of iron dissolution. And as we all know, EIS is such a complicated technique, so difficult to interpret. There's so many possibilities. It's so ambiguous that it occurred to me that maybe we could try to confirm some of her findings by using some of the capabilities that existed in Professor Marcuse's group. And that's where, through Huiru and Lun Tao, we approached Professor Marcuse and asked him if we could kind of conduct a parallel study on mechanisms of iron dissolution, parallel to what EIS was showing us with Negar's work. And he was responsive to it. So he can tell you the rest.
Yeah, perhaps I should give some background on the objective of the research we are doing. As we all know, corrosion may lead to failure of large systems and structures like ships, airplanes, bridges, chemical plants, oil and gas pipelines. But however, corrosion is a surface reaction, and the chemical and electrochemical reactions take place at the nanoscale. And we in my group in Paris tried to understand corrosion mechanisms at the nanoscale using advanced surface analytical techniques combined with electrochemistry. These techniques include scanning tunneling microscopy, X-ray photoelectron spectroscopy, time-of-flight secondary ion mass spectrometry. So we usually look at passivity breakdown, initiation of localized corrosion, inhibition of corrosion. So to block and to avoid corrosion, we look at new alloys like multi-principal element alloys or high entropy alloys, and that was actually the topic of Lun Tao's PhD in my lab. We also look at organic molecules for corrosion inhibition, but in all cases, we are interested in the mechanisms at the nanoscale, and we are also very interested in the early stage of corrosion because we think, I think there is good evidence for that, we think that the early stage govern to a large extent the evolution of the material later in a given environment. And so under the circumstances that Surgeon described, that sort of by chance, Lun Tao had finished his PhD. He was doing a postdoc. He was using time-of-flight sims for other purposes, and Huiru was working not far from my lab in Alain's lab. So we decided to combine our two approaches, which are fairly different and therefore quite complementary. And we used some of the techniques we are using, in this case, time-of-flight sims, to look at the mechanism of dissolution of iron in CO2 containing water. And we also looked actually at the way to inhibit corrosion, which was part of the program that was run in Surgeon's lab in Ohio.
So does anyone else have anything they'd like to add to the background to this collaborative study? Any of the other investigators who were involved before we go on to the next item?
Maybe I could add very quickly that iron dissolution has been a very rich and exciting topic for many years. And here at Lee's laboratory, a very ambitious model has been proposed about 40 years ago by one of my former colleagues, Professor Kedam. And it was very exciting and very rich work, but it was related to iron dissolution in aqueous solution in the presence of chlorides, which is obviously quite interesting as a starting environment. But obviously, 40 years later, research has changed a little bit. And what is new with this work, the one published in this two-part paper, is that we now focus on iron dissolution still in aqueous environment, but in the presence of carbon dioxide. And obviously, this is a new aspect of the work that brings new questions to the old mechanisms that have been proposed a long time ago. And so one of the purposes of this work is to understand a little bit more what is the real mechanism for iron dissolution and mild steel, because actually this is also a change in this work. We focus on mild steel instead of pure iron. And obviously, as a consequence, the mechanisms have to be evaluated again, and probably some changes are needed. And so it's good for me and for my lab and for my colleagues to see that a research that started 40 or 45 years ago is still useful, even if it's only the basis of the research of today.
Well, thank you very much for that comment. You're exactly right, of course. Iron dissolution has been studied for a long time. You mentioned 40 years. Actually, I think the work
it's older than that.
Work I published, I think, was done over 50 years ago. Yeah. But look, I didn't want to get into that. Let's go on to the next item. So the challenges and benefits of collaboration is something I've been interested in for quite some time, and I think the readers of Corrosion might be interested too. You folks collaborate over long distances, and no doubt there are lots of benefits, and you mentioned using complementary techniques. And is there anything we could add about, the challenges of collaboration? Not to mention, the different time zones you're on and arranging conference calls when both are awake, and the benefits of collaboration, which no doubt are immense.
Well, if I may just start answering that question. But before I do that, Winston, if I could add in this business of iron dissolution, which is the main topic here, as we all know, is very important, has been tackled for a long time, mostly by electrochemical studies. And these electrochemical studies, including one by Kedam, there are so many complicated steps and so many so-called intermediate species that show up and kind of disappear in the process. And I was always curious, since I was a student, is how do they know that these species are really there? I mean, you get some electrochemical results, but then, the rest seems to be kind of made up out of nothing, out of speculation. So when this opportunity appeared with Professor Marcuse that we could actually try to see if these species are really there, I thought that was fantastic. So when we talked to the students at that time, Negar and Huiru and Lun Tao, I think that was so inspirational to actually connect something we imagined was there based on electrochemistry with something that Professor Marcuse and one can really actually measure and say, yes, it is there, or no, it is not there. So that's kind of the gist of it from my point of view, which really made this whole study special. And in the end, we did confirm that those species we speculated about and Kedan speculated about and Bokris and Heusler speculated about in the 50s, that they were all there. They were right. And we were very happy to be able to directly confirm that. So, sorry for the digression, but I just wanted to add that in terms of kind of a simple explanation, what was the motivation for this collaborative study.
And thank you for mentioning that. It's a very important point. In the old days, 50 years ago or more than that, a lot of the species were purely thought processes, more or less.
Yes, and if I could add to that, just to complement what Sergeant has said, indeed, when we want to go from some sort of speculation based on the feat of electrochemical data to hard facts, I think it's very useful to use extremely surface-sensitive techniques like time of flight SIMS, which allows us to really observe and see, as Sergeant said, the species. So in that work, we could really look at very small amounts of adsorbed hydroxide ions, chloride ions, and also complexes between iron and these anions, and in such a way confirm and bring additional information on the mechanisms of iron dissolution. We could also do that in the early stages. So, for example, we could observe that the dissolution is not uniform. Actually, it starts locally, and we could observe the presence with the top SIMS imaging, chemical imaging capacity. We could look at areas which are dissolved, where the chlorides were located, whereas on other parts of the surface there were more hydroxide, and then gradually the surface becomes nearly fully covered by chloride. So we move from, say, localized corrosion to a more general type of corrosion. So that could allow us to discuss sort of speculative mechanisms that had been proposed in the past, as Sergeant explained.
Very good points, yeah. So are there anything else about challenges and benefits of collaboration? Certainly collaboration has increased immensely over the last few decades, say, like, going back to an earlier era, the research seemed to be really centered at particular places. Collaboration in those days was not nearly as extensive as it is today. And I just wondered, are there any other views on the challenges of collaboration or the benefits of it?
Well, I think that there are different challenges. There are always, when you collaborate, there are always challenges on the definition of the way we will do the experiments, because we don't do. If you look at the big rigs that Sergeant is using in Ohio, and we look at very well defined surfaces, very small samples. So we had to design experiments that from our perspective would bring significant results, and from Sergeant's perspective would be also results representative of larger systems. Other challenges is, of course, when we discuss the results, because there might always be some sort of bias from the beginning, and that's the also benefit of the collaboration, is we have all to sort of possibly revise some preconceived ideas that we may have had by confronting our ideas. So that's another challenge, and also a huge benefit, I would say.
Yeah, that's the difference between having a hypothesis, I guess, and having an objective. The hypothesis might link in with a person's own views before starting the research, but the objective might be less subjective, so to speak. Okay, anything else about this?
May I add some challenges? What I think? Yeah. So the challenge I see, except for the challenges Dr. Marcus talked about the experimental, I also see some challenges from the organization point of view. So because this collaboration is between 3 institutions with completely different backgrounds, so there's a lot of differences. These differences will bring different perspectives, opinions, and emphases. So which is a good thing to open our mind. But indeed, this gives us a lot of challenges. So to put everyone in the same page and unify everyone's opinion. For example, before the collaboration really started, we organized at least 5 project proposal discussion meetings even before the starts, and all the meetings are between the 2 continents. So which means across the time zone. So this indeed give us some challenges to make it happen. And even the paper writing took us almost 2 years, I think, because we need to read it over through everyone. And there are a lot of meeting discussions in between. Thank you.
All right. Well, thank you for adding that perspective. It's very, very interesting. Okay. Anything else to be added on this subject while we're at it here?
Yeah, if I may just add on the organizational side of things. Yes, Winston, things have changed dramatically over the past 5 years, let alone past 10, 20 years in terms of ease of communication. But I think there is a difference between the ability to easily communicate and actually collaborate. So I think nothing would have happened if we didn't have Negar and Luntao and Huiru, who kind of physically carried that knowledge back and forth between the 2 groups and spent time in one lab and came to the other lab and pushed us senior people to kind of talk to each other actively. So I really think that sort of good old-fashioned face-to-face interaction that happened as Luntao and Huiru traversed the Atlantic was essential to kind of bring this all together. Of course, they also, as I said, pushed us to finish write-up of the papers. That took us forever to kind of go through the dozens of iterations.
Well, thank you very much. That's very, very interesting and very important about the organizational differences. So anything else to add on this subject, the pre-meetings that take place? So then we can go on to the next item here. The objectives of each of the 3 different groups and of the 7-member team as a whole. We've talked around this a bit already. Is there anything more you'd like to add? So the objectives of each of the 3 different groups. I guess there's more like 2 different groups, really. There's the group in the U.S. and the group in France. But the objectives of the different groups and then the objectives of the team as a whole. Is there anything you'd like to add about that?
Well, if I may add a little context, we have been looking at mechanisms of iron dissolution for a long time, and probably for the past 30 years, everyone has, or most people have been adopting the so-called Bockris mechanism, which has been postulated in the early 60s as being valid for all acids, strong or weak, this or that. And there was a serious issue that, sometimes that proposal, that model by Bockris would fit in other cases it wouldn't. There is the study that Alan mentioned by Kedam from the 70s, which seemed to have been much more sort of powerful, and that is what we picked up. We picked up on that lead, on that study from Lys in Paris from the 70s, and tried to adapt it. Negar worked on that and tried to see, is it valid for weak acids, for CO2 solutions, and also in the presence of chlorides. So that was the context. Now, why did we do that? Because we need to understand the behavior of iron dissolution as the main anodic reaction in corrosion, as much as we do of the cathodic reactions, which have been studied far more. And that was kind of the push for Negar to apply her EIS to that. Negar, I don't know if you want to add something to that.
Yes, as Dr. Nessig mentioned, we were inspired by the pioneer research of Dr. Kedam and Bisky back in 1981, particularly their in-depth EIS analysis, which was for island dissolution in sulfate-containing environment. But we tried to extend it to dissolution in the presence of CO2 and sodium chloride, and building upon their work, we extended our study to understand more the behavior of this reaction in these environments. And that's helpful, in order to understand this mechanism and try to build models based on that, which can be used in the future along with the mechanism of the cathodic reaction to predict the corrosion rate in such environments.
Yeah, and I think I have already described the objectives of the work we are doing in my group, and also the method. So very clearly there was a convergence with what the group of Sergeant Nesic was interested in, by looking at mechanism of corrosion of iron at a scale which is amenable by the techniques we are using, where we can really look at small amounts of adsorbed species, essentially hydroxides and chlorides and oxychlorides at surfaces. So that fitted very well our objectives together with the topic of behavior of steel in the oil and gas industry and transportation.
Is there anything else on this topic of objectives? We can go on now to the main achievements of the study and why these are important. I think we've touched a bit on this already, but it would be worth maybe just running through the main achievements of the study and why these are important.
Well, I've been speaking too much. Maybe one of the younger researchers should take that up. Like the leading authors, maybe Negar and Wiru. Maybe you can try.
Okay. For this, I think it's the first time we use a top themes that is really powerful surface analysis technique to study the iron dissolution mechanism on carbon steel. And also the 3D images is a really powerful technique which was first be used to study this kind of the mechanism. And we really see the parallel mechanisms, reactions that we see the iron hydroxide formation and iron chloride intermediate formation during this process by the 3D images. And also we can, I think it's for the other researchers, they can also trying to use this powerful technique to study like CO2 corrosion on carbon steel on the other subject. Yeah, I think this open a door for the other researchers on how to using this powerful surface technique to study some mechanism on carbon steel CO2 corrosion.
Negar, do you want to say what we achieved with EIS?
So EIS was very useful for us in this research because this mechanism is far away from being a single reaction. And it's a multi-step reaction, and this reaction you can be actively dealt into that using the EIS. And we try to understand the behavior of iron dissolution in the presence of the CO2, and we try to propose a modified version of Kedam's mechanism to actually show how this reaction works, different environments having sodium chloride or CO2. And as I mentioned, this mechanism can be used in order to model this iron dissolution, and that can be implemented for future study when we want to, for example, predict the corrosion rate in such environments.
And if I may, to summarize, I think the main achievement of this work. So it's in this study, both the theoretical work, the modeling work, and experimental work with totally different instruments at very different scales will combine together to rebuild the multi-pass, the mechanism of anodic iron dissolution reaction. So this is this fundamental work provides new insights into the anodic iron dissolution reaction mechanism for the mild steel in this chloride containing CO2 environment. Thank you.
Okay. Well, thank you for that.
Yes, if I may summarize maybe some of the major features, and I think it was very exciting. I think it was to make a direct observation of the chemical species, especially hydroxide ions and chloride ions on surfaces, to be able to prove that there is really a competition between adsorption of hydroxide and chlorides, with chloride gradually sort of winning the competition. And this increase in chloride concentration explains the fact that we, in time, go from localized corrosion to a more general corrosion. We could even observe by looking at the surface roughening, which we can observe by time of flight 6, which of course can be measured directly also by atomic force microscopy, which is one of the specialty of Alain. We could also follow the surface roughening, and finally we can show that there was no formation of a stable complex with carbonate. So this is perhaps something that remains a little bit puzzling, is that it seems that carbonate is sort of enhancing the effect of chlorides without reacting strongly with the iron surface.
Maybe just one comment. So first of all, the main goal of the study was to directly identify the OH and chloride containing species. And thanks to the first top sense measurements, we observed some strange things, especially at the interface between the oxides and the metallic substrates. And that's why we decided to try to have some 3D imaging on the surface, and where we observe the pitting degradation first of the surface, and then the more generalized corrosion with time. So it has been done in 2 times. First, direct evidence of the different species, and then 3D imaging to have access to surface degradation mechanisms.
Well, thank you very much for that. Anything else about the main achievements? We can go on to the next.
Yeah, if I may try to also kind of summarize, going back to the objectives, we wanted to see how does this iron dissolution happen, and the idea from the 60s was that there is an effect of hydroxide, and then later on also of chloride, and as I said, I think this is one of the first times that those presence of those intermediate species, those complexes, were directly proven by using TOF SIMS. However, we have electrochemically observed that CO2 affects the iron dissolution, but shouldn't be forming a surface compound. That was a speculation that came from Negar's work. She thought that somehow it changes the rate of dissolution, but it doesn't form any new intermediate species. And astonishingly, I think for me, that is exactly what TOF SIMS has observed, that there were no carbonates, like Professor Mercou said, on the surface. So of course now the question is, how do they do it? How do carbonates then change the iron dissolution if they are not forming compounds on the surface? But as every good piece of research, it poses new questions which we have to answer. It doesn't only answer everything. We have new challenges now too.
Okay, so we'll go on to the next item, which is to whom are the 2 papers in corrosion addressed? Now, I noticed that the first paper on EIS was supported by a who's who of companies in the energy pipeline business. So there's probably quite a wide readership of these papers among those, that large number of sponsors, all of whom use steel pipelines. And guess what? Those steel pipelines do corrode, and they're being replaced by more steel pipelines. So anyway, it's certainly an area where this type of knowledge is essential. And the part 2 of the paper was supported by the European Research Council and National Science Foundation and the Région Île-de-France. So would there be anything you'd like to add about the readership of these papers, which I imagine will be quite extensive, and I think they'll be highly cited, actually?
I think that our work is highly relevant for anyone who deals with corrosion of steel. And that's a very broad audience, including the companies, including the oil and gas companies who have graciously given us this latitude to pursue such fundamental work. Yeah, but I think the applications are very, very broad. I mean, not only on pipeline steels, but corrosion of bridges, of any type of steel, and the mechanisms associated with it. So I hope the readership is going to be quite broad. Yeah, due to the nature of these papers, I think the audience will be more on the research side of things rather than the sort of practitioners. But so be it. One has to start somewhere. Sorry, Philippe.
Yeah, no, I fully agree. I think that clearly because we are uncovering fundamental mechanisms, the readership should be primarily researchers from academia, but I'm also convinced that people doing research and development in the industry will also be interested. So I would expect a fairly broad audience, but only the future will tell us.
Well, it's an impressive list of sponsors if you put the whole thing together. That's for sure. Anything else on that one? So the last thing I thought we might look at is the objectives of continued collaboration, future challenges to address beyond this study. So is there anything that you folks would like to add about, where we go from here to address future challenges? And I guess we mentioned a bit earlier the follow-on research. Like every good research project, I guess, brings up questions that then have to be answered. So there's more research projects. But anything specific that you'd like to chat about just now?
Well, from my perspective, I would say that obviously this was a very fruitful collaboration, and the complementarity between the approaches in the US and here in Paris is very good and very powerful. So hopefully there will be a continuation, and we have discussed some possibilities along the same line as what we have been doing, or maybe other subjects where we could probably combine not only our approach, but even more applied goals in the time where we are moving from CO2 producing energy to CO2 free emission system. So there are a number of possibilities. Now it also very much depends on the human resources, and because surgeons pointed out that everything was made easy to some extent thanks to the younger researcher who happened to be in Paris but working in the different labs. So collaboration is not just something you decide. I mean, like surgeon and I have known each other for many years, and we have discussed, we have had scientific discussions, but before we really go into a collaboration, it took the sort of favorable context that he described.
Yeah, just to complement what Philippe just said, and also Alan. I think this work, which I think is quite novel, kind of points out how many benefits can be reaped when different groups really get together. Alan from one laboratory in Paris, Philippe from another, and then Antoine, and then us on this end, with very strong preconceived notions of how things really happen, and that's kind of bringing together of minds, particularly backed up by the Excel students who did all the hard work. I think this whole study and the whole collaboration is sort of a model, like Luntao said, for what can be achieved if different groups and different techniques are brought together and kind of made to discuss and try to kind of figure out what goes on. So I really hope we will continue with that. I'm actively looking for another young student or students who we could send to Paris and to continue trying to benefit from this multidisciplinary collaboration. I would say there are some open questions that these two papers leave, like, for example, what is the role of CO2 if it doesn't form carbonates on the surface? What does it do? I mean, it's a very simple question. It seems to be the hint is it does something through its interaction with chloride, but what is the question? So I think there are questions like that may be subject of the future research, or like Philippe said, it may be something completely different. Also with Alan, we are exploring other techniques in addition to these two, like AFM and EQCM, and a combination with DIS. And I think these multi-technique studies are the way to go and really help tremendously in raising confidence that the results we get are actually meaningful.
It's really an amazing sort of development, I think, with this collaboration. Is there anything that anyone would like to add to this discussion? Any other comments on any of it?
All I can say is that I fully agree with what Serjan just said 1 second ago. It is obvious that a few decades ago, electrochemical impedance spectroscopy was a very promising electrochemical technique. But there was a lot to do at that time, because the measurement, the good measurement of an electrochemical impedance spectrum is not an easy task. And once you have a good measurement, you have to make sure you are able to provide a deep interpretation of the spectrum you get. And this required the development of a lot of theoretical models and equivalent circuits. And this was a lot of work that has been developed by many groups around the world. It's been the case here at least, but it's been the case in many other labs around the world and for decades. But at the end of the story, electrochemical impedance spectroscopy is a technique that provides information at the global scale. And we've already described the weaknesses of this technique. And obviously, nowadays, things have changed. And we show with this paper, but it's been shown in many other papers and with many other topics, that beside a very good and well-mastered electrochemical technique, what is needed is the coupling or the association of other techniques, some of which may still work at the global scale, whereas others will work at the local scale. And some of them will provide electrochemical information, but others will provide chemical information or topography information or mass variation information and so on. And when we focus on a very complex mechanism like iron dissolution in a complex aqueous environment, the association of all those techniques is required if we want to have a full picture of the story. And sometimes by doing this brings us back to the basis, and we have to make sure that what we want to interpret is actually well measured. It appears that in the case of electrochemical impedance spectroscopy, the measurement of the spectrum in the low frequency range is actually something quite difficult and tricky. And so it's like a loop. at the end. You start with electrochemical techniques and EIS, and then you bring new information with other techniques, and this brings you back to the measurement using electrochemical techniques. So we really need to. We really need those very important human relationships to work all together and to bring our different expertise so as to do all the steps very properly. But it may be some kind of loop mechanism at the end, because there are a lot of risks in such studies because the topic is complex. And so I think with such papers, I hope we will develop the excitation of people about this topic, and there is still a lot to bring. But what is true is that by the time we are having this very nice roundtable, we have a student, a visiting PhD student, talking about Camila, who's doing her PhD with Surgeon. And indeed, we are starting exploring new couplings that could bring us more information about this kind of mechanism, which is iron dissolution. So there's still a lot to do. I really hope we will do a lot all together, but I am sure, and I deeply hope that other groups will have new ideas as a consequence of our work, and probably they will also bring very important contributions.
Well, thank you very much for those comments. Is there anything else that anyone would like to add before? Yes?
Yeah, Philly, if I may just add one more thing. I mean, we were here focused on our research and how it came about and what was it about and what are the results and what is the future. But I want to say also one important, very beneficial thing emerged from this collaboration, and that is these young people who are here with us and the fact that we were able to expose them to these different groups. So Luntao and Huiru and Negar, the fact that they were able to work with me, but also with Philippe and with Alan and with Antoine, that has given them a depth that I could never, ever offer alone. And I think that is also another immense benefit from this collaborative work, is what we gave to the students and how we shaped them going forward.
Well, thank you very much for that comment, Sergio. You know, the educational part of this is certainly very important because, as we say, you know, the next generation is the group that's going to lead this this whole enterprise going forward and the research into this important area. Any other comments at all here before I have some final comments of my own, just to wrap up? Anything else at all that anyone would like to say? This is your chance.
I would be here for thanks for Professor Marcus and Professor Sojanesic, and both of you give me a chance for postdoc and collaboration with both of you. Give me a lot and let me learn quite a lot from the aspect of first surface analysis and also from the aspect of the CO2 corrosion. And I learned quite a lot. Now I'm working in China at USDB. I think we can collaborate in the future for both of you and also the Alan, and we can collaborate and to explore what we can do in the future.
So we can extend the time difference between the lab from 6 hours to 12 hours.
Well, you know, on the extending the hour, one of the things Bacchus used to say to his students and also his postdoctoral fellows, of which I was one at one time, and he said that in his lab, they work on an 8-hour schedule. It's 8 hours before dinner and 8 hours after. So that's just as an aside. Any other comments from anyone? This is a chance to say something before we wrap up completely here. Anything else, or anybody would like to add? Okay,
you know,
I have a couple.
You mentioned that there is a continuity there. One of Bockers's postdocs was Professor Drazik from Belgrade, and I am Professor Drazik's student. So I'm Bockers's grand student, as they said, and I guess Alan is Kedam's sort of student or young colleague. So there is a bit of kind of generational connection here. We've been starting with Bockrus's mechanism or Kedam's mechanisms, and here we are, the second and the third generation, tackling those same questions and trying to add to the wisdom they shared with us. So I think that's very nice.
Tremendous, yes, tremendous. So any other comments at all here before we wrap up?
I also want to express my appreciation to all my supervisors and advisors. So as I mentioned, I spent 3 years in Ohio University with my advisor, Dr. Dissolution, and I spent 3 years in Paris, in Sorbonne University with my supervisor, Dr. Alan Pivot. And when I was in Paris, I also spent almost 1 year with Dr. Philippe Marcus. So I think I'm very lucky. When I was so young, and I can get help from so many big people. So they greatly opened my mind and give me a lot of knowledge from different backgrounds and show me how to think, how to do things. I think it's very helpful in my future, and also I think in the future I will keep benefiting from this, and I hope this kind of collaboration can keep going on to help students and young scholars like me. Thank you.
Well, thank you very much for that. Anything else that anyone would like to add before we wrap up? I just have I have a couple of comments actually. On the, I would just like to add, many years ago, when I was in a different stage of life, one person said to me, take the opportunity to work somewhere in Europe, because when you do that, you'll learn how other people solve problems. Like we know how we solve problems here in Canada, but the Europeans are different. They solve problems differently. So take the opportunity to work in a faraway land. So that was just one bit. I would like to thank Sammy for asking me to moderate this roundtable. And indeed, it was my great privilege to have the opportunity to process this two-part paper through the corrosion review process and into print. And I'm glad that we were able to do it in a timely way. And I'm grateful, as an associate editor, I'm grateful for the many authors out there who work long and hard to prepare their papers. And I hope the authors are glad to hear from me when I get back to them with reviewers' comments and points that will help them to improve their papers before they go into print. So, unless anyone has any other business, I think.
Well, just also express my thanks to you, Winston, and to Sammy for putting together this meeting, and for all the technical staff. And I don't know who is going to edit, but I'm sure there will be some editing work before it can be made public. And thanks to all the participants. And I think it was nice to have the whole. That's the benefit of modern technologies, that we could the whole collaborative team could meet again. So thanks to all.
Well, I greatly appreciate this opportunity to bring the different generations of workers together here. So it's been fantastic. So thank you, Sammy, for coming up with the initial idea, I guess, of having a roundtable. It's really tremendous.
I also wanted to thank everyone, all the co-authors from France and also the US, and also the people from Corrosion Journal for having us. My PhD journey was amazing. It was joyful, and it was combined with such a good collaboration. And I wanted to thank everyone for that.
Well, thank you to all those involved with this work here. And we'll look forward to seeing the paper in the July issue of Corrosion Journal. So, thanks again.